Well, folks, it is January 5th, 2022, and there is no school today. And I am locked out of my Google Drive, and my email, and my classrooms. So, you know what? I figured we're not going to let today go to waste. I've been meaning to do this because what I've noticed is in this past week when we were doing the mole conversions review activity, with like the beaker of water, um, and like the cereals. Well, the cereals were for percent composition, but that activity. Okay, when we were doing that, I noticed that I had some students who either weren't here the week before winter break, which was a very important week to be here for actually, because that's where we did a bulk of the math practice, or just students who completely forgot how to do all this, which is perfectly fine. And granted, while you could go straight to YouTube and just type Khan Academy or any other random teacher, scientist, I mean, there are literally thousands of them on YouTube. I figured, I may as well just do one myself. I mean, I don't really have much else going on today. I can't log into my Google Drive. So, and you know what? You get the benefit of me going through how I would teach it. So, hopefully it's helpful. All right. We're going to do a bunch of different kinds of conversions, though, today. Essentially between these three units. Because when we do mole conversions, we're going between mass, which are in grams, moles, and particles, which can be atoms, molecules, or formula units. All right. I'm not going to really be going over in these videos conceptually too much about what a mole is. But as we work through the conversion factors, I'll give you some definitions and it should hopefully help. Okay, let's just start with this problem, all right? Now, we want to go from mass to moles, all right? I'm telling you that right now. I mean, on like a quiz or an exam, I would probably phrase it as a question. I wouldn't be like mass to mole, but here I'm just going to say mass to moles. How would we do that? Remember, it's essentially just dimensional analysis. And in dimensional analysis, you need one thing, and those are conversion factors. All right? That is probably when we do these mole conversions, it's probably the most difficult part, maybe, are conversion factors. So molar mass and Avogadro's number. Okay, those are going to be our two conversion factors. Now here we're just going mass to moles. So it's only a single step conversion, which is really nice for us because we won't even have to deal with Avogadro's numbers, and we also won't have to deal with particles. All we have to deal with are mass, molar mass, and moles. So, dimensional analysis problem, you always start with what? It's your given. You always start with your given. And I'm telling you that our given is 125.5 grams of sulfur dioxide, okay? So let's just write that out. 125.5 grams sulfur dioxide. Now, you're going to still need to know how to do this. I'm going to expect you to know how to, all your nomenclature, your naming conventions. Can you get from sulfur dioxide, the name, to the chemical formula? Okay, so we have our given. We're doing wonderful. Now we need a conversion factor, right? Remember, every time you do a conversion factor, I would just write the multiplication sign and then get that division, like, I don't know what you want to call it. I would write that first, okay? The second thing you want to do is, okay, well, now you have to think. What units do we want to go to, and what units do we need to cancel out? Well, we know that we want to get to moles, okay? We're in grams and we need to get to moles. How would we do that? Well, in our conversion factor, we need to first cancel out grams. Now, when we cancel out units in dimensional analysis, if you remember from the beginning of the year, we always put the same units across from each other, okay? That's how we cancel out units. And we're trying to get to moles of SO2, okay? Specifically here, we have 1 mole of SO2. Well, how many grams of sulfur dioxide are in 1 mole? How would you figure that out? The answer is right here. Your periodic table. Ignore the whatever ink stuff got on my paper. All right. Molar mass is literally just adding up the masses of each individual atom in the compound. And I'm just going to do the math for you right now. I'm going to tell you that sulfur dioxide weighs 64.064 grams. If you don't know how to get this number, molar mass, then I really recommend looking at the slide deck. Okay? I have one slide in the presentation that goes over exactly how to do this. All right, nice. This is all we have to do. We have it completely set up. I mean, it will help to cancel out units here, right? I mean, we're done with grams. So now it really is just 125.5 times 1 over 64.064. If you understand what this represents, it literally is just 125.5 divided by 64.064. All right? And the number you should get is 1.95897. What's wrong with that? Well, the issue with that number is that we didn't account for sig figs. All right? Now, if we're looking at sig figs here, we have 4 sig figs in our given, and we have 5 sig figs in our molar mass. All right. When we do multiplication and division, you're literally just using the least number of sig figs. So we want 4 sig figs, and our answer here we want 4 sig figs. 9 is bigger than 5, so we know that we're going to round up, right? I'm going to write that little plus sign just to like kind of represent that we're rounding up. And the answer you should get is 1.959 moles of SO2. There's your answer. I do want to clarify just one thing, though. Just one last thing, just so you're really aware of this, okay? Now, our conversion factor, okay? This is the main thing I want drilled into your head. Our conversion factor, 1 over 64.064, is literally the molar mass, right? We got this from the periodic table. It's just the molar mass. Whenever you go between mass and moles, or even moles to mass, you're going to need molar mass in your conversion factor. Okay, I wanted to do one last conversion of mass to moles, and mainly just to illustrate one concept that you don't want to mess up. All right, let's look at our scenario. We have 12.6 grams of chlorine gas, and I want to get that to moles. So what do? We always start with our given, right? 12.6 grams chlorine gas, Cl. What's wrong with this? Well, the answer is right here, chlorine gas. When you do any type of mole conversion, you always need to have in the back of your mind our favorite, Hunkelbrief, the diatomic molecules, right? Remember, each one of these elements in Hunkelbrief are found naturally, or in nature, they are found as diatomic molecules, which means there are 2 of them bound together. So when I say chlorine gas, I don't mean just chlorine, I mean Cl2. Why is this important? Because when we do our conversion factor now, remember we're going mass to moles. Okay? We're going to need the molar mass. When we go from mass to moles of chlorine gas, we need it to be diatomic, and the weight of a diatomic molecule is twice the weight of just the element alone, right? Chlorine weighs 35.453. If you look at this right here, chlorine weighs 35.453 grams per mole. But we have 2 of them. So we need to multiply that number by 2. So it's really 70.906 grams. All right? And that's it, right? We can just cancel out the units now, get rid of our grams. And if you do the math, you should get 0.1777. We need to account for sig figs. We have 3 sig figs here, 5. So we know we need 3 sig figs. So our real answer is 0.178 moles of Cl2. That's it. Okay. Do not forget Hunkobrief. Okay, I think we have a pretty good basis in this dimensional analysis, so we can probably work through this one a little bit quicker. All right, but there is a difference in this problem. We're going now from moles to mass, right? Moles to mass, and I gave you our starting mole. 9.46 moles of copper 1 fluoride. All right, so we always start with our given. 9.46 moles. Copper 1 fluoride is just CuF. And let's get that dimension or that conversion factor set up. Now remember, we're going moles to mass. We still are going to use molar mass as our conversion factor. It's just going to be flipped, right? Because if moles are in our numerator here and we need to cancel out moles, 1 mole CuF, right? We have to cancel out moles diagonally. What's going to go in our numerator? Again, this entire conversion factor here always represents molar mass. So we need the molar mass of CuF. Where do you get that? Periodic table. And I'm going to tell you right now that it is 82.544 grams. Lovely. We can cancel out units. I'll write CuF up here. And that equals 780.86 grams. What's wrong with that? Well, we have 3 sig figs here, 5 sig figs up here. We don't count 1 mole CuF as a sig fig. So our real answer, after we round, should come out to 781 grams of copper 1 fluoride. See, it's kind of nice. It's only a single step conversion. All right, here's our new scenario. Now I'm telling you that we want to go from moles to particles, right? So let's look at our little triangle up here. We're starting in moles, and we need to get to particles. So the nice thing is that we don't need molar mass anymore, and we don't even need to deal with mass. It's just moles to particles. What's our conversion factor? It's Avogadro's number, right? 6.022 times 10 to the 23rd. All right. Dimensional analysis, what do? We always start with our given. And I told you that we are starting with 3.45 moles of potassium dichromate. Potassium dichromate, I don't know how to write that. Well, if you don't know how to write that, then you need to get studying that nomenclature again. Potassium dichromate is K2Cr2O7. That's 3 elements, and I mean 2 potassiums, 2 chromiums, and 7 oxygens. That'd be a pain in the... Well, it'd be a pain to get its molar mass, so I guess be grateful that you don't have to do that. Anyway, we want to get moles to particles. We have the conversion factor set up ready to go. What do we put into it? Well, we know that we're canceling out moles diagonally, so there's 1 mole K2 Cr2O7, and the numerator. The numerator, again, our conversion factor is Avogadro's number, so our numerator is really just 6.022 times 10 to the 23rd. Now be careful here, all right? Do not write the word particles. We are going to particles, but because this is potassium dichromate, we need to be specific of what kind of particle it is. Remember, there are atoms, molecules, and formula units. Atoms represent pure elements. Molecules represent covalent compounds, which are two nonmetals bound together. You know them as type 3. And then there are formula units, which represent ionic compounds, which is a cation and an anion. And right here, I can tell you right now, we have a cation and an anion. So these are going to be formula units. And writing the word formula unit is too annoying, so we're just going to say FU. F that. All right, we can cancel out units now. I mean, we're done with moles. And now we're just in formula units. It's literally just multiplication. 3.45 times 6.022 times 10 to the 23rd. And the answer you should get is 2.077 times 10 to the 24th. We need to account for sig figs. We have 3 sig figs is the least number. So it's really 2.08 times 10 to the 24 FU, do not forget units, of potassium dichromate. So we didn't have to use the periodic table, but you do have to remember Avogadro's number. All right, let's go now from particles to moles. The nice thing is that we're still using the same conversion factor, Avogadro's number, and we don't need to use molar mass or mass because we're just going particles to moles. Let's start with our given. We have 8.75 times 10 to the 25 molecules of carbon dioxide. And the key word there is molecules. Carbon dioxide, CO2, are 2 nonmetals, right? 2 nonmetals. That's a covalent compound. Any covalent compound, we're going to refer their particles to their particles as molecules. All right, but anyway, let's just jump into the math, and what do we start with? 8.75 times 10 to the 25 molecules of CO2. Wow, that filled up like half the board. All right. Conversion factor time. We are trying to get to moles, and we know that we need to use Avogadro's number. Well, if we have molecules in our numerator here, then to cancel it out, it has to go in our denominator, right? Cancel out units diagonally. So 6.022 times 10 to the 23rd molecules of CO2. And we want to get to moles, so 1 mole of CO2. I mean, conceptually, if you just think about this, we're saying that in a single mole of carbon dioxide, there are 6.022 times 10 to the 23rd molecules of carbon dioxide, right? But our given is that in our given, we have a lot more than a single mole's worth of carbon dioxide. So that's why we have to do a little bit of math here. Let's cancel out our units. Now we're in moles. If you plug this into your calculator, you should get 14.53 moles. We need to account for sig figs. Least number of sig figs here is 3. So our real answer is 14.5 moles of CO2. Right? We're saying that 8.75 times 10 to the 25 molecules of carbon dioxide equals 14.5 moles of CO2. All right, let's do a little bit of more difficult math. Even though, honestly, it's the same thing. It's the same thing what we just did. The only difference is that when we go from mass to particles, you can't just go in one step. The triangle doesn't connect at the bottom. Sorry, folks. Doesn't work like that. So when we go from mass to particles, we need to stop at a pit stop. And that is known as the mole. So we're really just doing two different conversions, right? We're going mass to moles and then moles to particles. If you don't remember how to do any of those, refer earlier into the video on how to do those types of conversions. So let's just start with our given here, right? We have 8.25 grams of tin 2 nitrate. And what am I going to do? I always write our given. Tin 2 nitrate. Well, tin 2 nitrate looks like SnNO3 2. Okay, this is going to have a little bit of this is going to be a little bit more of a time-consuming molar mass to figure out. I'll be honest. Okay. Now, remember, we're trying to get our end goal is to get mass to particles, but we need to stop at the mole. So mass to moles first it is. Okay, well we need to cancel out units. We know that our denominator is going to be grams, right? Because grams are in the numerator in our given. Tin nitrate. Okay. I'm going to write 1 mole because, remember, this conversion factor, molar mass, we're saying how many grams of tin to nitrate are in a single mole. I'll do the math for you, and I'll tell you right now that it is 242.719 grams. All right. We can cancel out units now. But we're not done, right? Because we're in moles. And we want to get to particles. So what do we have to do? We have to do another conversion, moles to particles. And we're going to be going through Avogadro's number to do that. So I'm sorry if this makes it look a little bit confusing, but we're going down here now just because I don't have enough space here. Moles in our numerator here, we need to cancel it out diagonally, so we know that our denominator here is going to be 1 mole of tin 2 nitrate. By the way, I mean, I don't know if I have to reiterate this in case you forgot. The 2, the numerator, that represents the charge of tin, right? Nitrate has a charge of 1 minus. Maybe it'll help you to see tin NO3 1 minus. Anyway, okay. Well, Avogadro's number is always 6.022 times 10 to the 23rd. Now, units. Tin 2 nitrate, what kind of compound is that? It's ionic, right? Cation, anion. When we deal with ionic compounds, our unit is Fu. Now we need to cancel out units again. We're done with moles. And now we're in particles, FUs. So if you plug this all into your calculator, by the way, when you do plug it into your calculator, you can do it in multiple steps. I think maybe that ensures the likelihood of you messing it up to be lower, but I don't know. Anyway, if you plug this into your calculator, you should get 4.5279 times 10 to the 22. This is too many sig figs. It looks like here in all this, the least number of sig figs we have are 4. So we will need to do a little bit of rounding, right? Yeah. Okay. And we are going to get 4.528 times 10 to the 22 FU of tin to nitrate. We're running out of space here. Okay, but you kind of get what I'm writing, hopefully. Yeah, so we went from mass to moles and then moles to particles. And if it helps you just to see that again, maybe I'll write right here. This our first conversion factor was mass to mole, and our second conversion factor was mole to particle. In this case, our particle we were dealing with was FU. All right, just one last conversion, all right? And this time we're going from particles to mass. Particles to mass. Again, we can't just jump between the two. We're going to need to go from particles to moles and then moles to mass. So we're just working in reverse in comparison to the last one I went through. What's our given here? We know that we have 7.29 times 10 to the 22 particles of lithium. I didn't want to write down what kind of particle because I want you to think really quickly. What is lithium? Well, lithium is a pure element, right? It's just old lithium. And when we're talking about just a pure element, assuming it's not a diatomic molecule, remember Hunkelbrief, then it's going to be atoms. Right? Lithium is not a part of Hunkelbrief. Lithium is not a diatomic molecule. So, let's start with our given. 7.29 times 10 to the 22 atoms of lithium. And we need to get that to what? We're starting with particles. We need to get it to moles. And we're going to use Avogadro's number to do that. Dimensional analysis, we cancel out units diagonally. So we know that atoms for sure has to be in the denominator here, and our numerator for sure has to be 1 mole of lithium. We're saying, remember conceptually, that in 1 single mole of lithium, there are 6.022 times 10 to the 23rd atoms. Right? Conceptually. I don't think I have enough space over here, so I'm going to move down to the bottom. And I actually forgot really quickly, we should cancel out units. So we're done with atoms here, and now we're in moles. Well, if mole is in our numerator here, in this conversion factor, and now we're going moles to mass, we're going to put 1 mole of lithium now in the denominator, because it needs to cancel out with each other. 1 mole of lithium, how many grams are there? If you don't know, again, remember, molar mass you find right on the periodic table. Lithium's is 6.941. So 6.941 grams of lithium. We can cancel out units, right? We're done with moles. Goodbye, mole. And now we're in mass. And we're done. Plug it into a calculator, and you should get 0.8402. That's not accounting for sig figs. We know the least number of sig figs here is 3. So it really should be 0.840 grams of lithium. And that's it. That's how you do all conversions. Hopefully that was helpful. And hopefully I didn't mess up any of it at any point. I don't think I did, but let's hope it all went okay. All right. Adios.